Unit SP12 Magnetism and the motor effect. Recall that unlike magnetic poles attract, just like that, and like magnetic poles repel. So a north repels a north, a south repels a south, and a north and a south will attract. Describe the uses of permanent and temporary magnetic materials, including cobalt, steel, iron and nickel. Well, the first thing is, make sure you know that they are the four magnetic materials that you'll need to talk about at GCSE. And the uses, well, the uses of permanent magnets. For 1 mark, you use them in a fridge door, or for separating recycling, like steel cans from aluminium cans. And uses of temporary magnets could be maglev trains, which is magnetic levitation trains, and electromagnetic cranes found in junkyards and places like that, where they've got to move metal from one place to another, and they use temporary magnets. What they mean by that is electromagnets, so they can turn them on and off. Explain the difference between permanent and induced magnets. So a permanent magnet is always magnetic. Well, that's easy, isn't it? It's always got a magnetic field around it. But an induced magnet, they are only magnetic when in another magnet's magnetic field. So if you just had a piece of iron, it wouldn't have its own magnetic field. But if you put that piece of iron next to a magnet, it'll gain its own magnetic field from the permanent magnet. So the permanent magnet goes north-south. The induced magnet would also be north-south. So make sure you do the north next to the south. I've got videos on my YouTube channel in all these different playlists. If ever you need any extra help, check out the full videos. Describe the shape and direction of the magnetic field around bar magnets and for a uniform field, and relate the strength of the field to the concentration of the lines. Now that's what I've just explained with the electric fields. So with a bar magnet, you've got the lines are closest where the poles are. So the magnetic field is strong here because the lines are close together, exactly the same here. And the magnetic field is weak on the outer edges over there and over here, further from the magnet. And that's because the further away from the magnet you get, the weaker the magnetic field is. We represent the strength of the magnetic field by the lines. And the magnetic fields come out of the North Pole and go into the South Pole. Describe the shape and direction of the magnetic field around a bar magnet and for a uniform field. So for a uniform field, you'd have this plate here and this plate here, which are parallel to each other. And you'd have a uniform magnetic field lines equally spaced out, going from the north to the south. Notice around the edges here, it's not quite uniform, so it's just this part right in the middle between the two poles. Describe the use of plotting compasses to show the shape and direction of the field of a magnet and the Earth's magnetic field. So the field around a magnet, what you basically do is just put plotting compasses all over the place. You can see I've strategically placed them to show that the field comes out of the North Pole and goes into the south. So these compasses here would show the shape and direction of a magnetic field. And what you do is you just, whichever way the compass is pointing, draw a little arrow coming out of the compass on the paper next to it. Little arrows coming out like that. And then you just connect all those arrows together there, connect all these arrows together there, and just do the same coming down that way. I've got a video that shows you how to do it if you don't understand what I'm talking about. And the Earth, where the North Pole is and the South Pole is, there's exactly the same field coming out of the Earth. But obviously it's not horizontal like that. The poles would be vertical. Explain how the behaviour of a magnetic compass is related to evidence that the core of the Earth must be magnetic. Well, basically, a compass points to Earth's North Pole. That'll get you 2 marks. Describe how to show that a current can create a magnetic effect around a long straight conductor, describing the shape of the magnetic field produced and relating the direction of the magnetic field to the direction of the current. So you want to use the right hand grip rule for a straight wire. So point your thumb up, point your fingers round like that. Your thumb shows which direction the current's going as it's going through the wire. In this case, the current's going upwards. And the fingers would show which way the field goes. Now the magnetic field direction is from north to south, same as usual. Knuckles is north and fingertips is south. So if you pointed your thumb up, your fingers would come around in a circle like that. If you were looking down on it, it would be anti-clockwise. And the current is conventional current, which is from positive to negative. Recall that the strength of the field depends on the size of the current and the distance from the long straight conductor. Yep, if you increase the size of the current, that'll make it a stronger magnetic field. And if you are closer to the wire, you'll have a stronger magnetic field. So a strong magnetic field next to the wire and a weak magnetic field as you move further away from the wire. You can see these lines here are close together, but these lines further apart are further apart. We always use the lines to represent the strength of magnetic and electric fields. Explain how inside a solenoid, so that's an example of an electromagnet, which is basically just a coil of wire. That's what a solenoid is. The fields from individual coils add together to form a very strong, almost uniform field along the centre of the coil. That's that there. And they would cancel out to give a weaker field outside of the coil. All right. So the magnetic field from here interferes with the magnetic field out there. And you end up with a weaker field out here and a weaker field out there. And nice and strong in the middle. And you'll notice, yes, it's nearly uniform because these yellow lines that I've drawn for the magnetic field are nearly parallel to each other. Notice that the right hand grip rule for the solenoid is different to the right hand grip rule for a straight wire. The thumb this time doesn't represent the current, it represents the direction of the magnetic field, and the fingers this time represent the current, where the current's going. So the current's going from the front of the screen to the back of the screen, front of the screen to the back of the screen. Well, you can see these fingers are coming from the front down to the back. But it's only worth 1 mark, so you'll not need to know that. Recall that a current carrying conductor placed near a magnet experiences a force and that an equal and opposite force acts on the magnet. Well, that would be the same as placing 2 magnets together. So if you placed a magnet inside this magnetic field, it's going to repel or attract. Explain that magnetic forces are due to interactions between magnetic fields. Yeah, that's just a statement. Recall and use Fleming's left-hand rule to represent the relative directions of the force, the current, and the magnetic field for cases where they are mutually perpendicular, which means all at 90 degrees. So Fleming's left-hand rule is this here. Your thumb represents the movement, first finger represents the magnetic field, second finger represents the current. I've got a nice video on that if you want to know more. Use the equation F equals Bill. So that's the force on a conductor at right angles will equal the magnetic flux density times by the current times by the length. So if it is on your exam, they'll just give you the equation and the numbers and just pop them in. So best of luck with your exams and good luck for your future. Work hard, be nice, and bye for now.